In this lecture, we're going to look at what we call the relative importance of resonance structures. And what I mean by this, and the reason I put it kind of in quotes, is that sometimes we have a series of resonance structures that we've drawn out, and some of them are less important than others. And when I say that, again, what I mean is um, they don't contribute as much to the overall description of the structure of the compound, the whole thing. Kind of think of it like if you were to create a hybrid fruit that is like 95% apple and 5% peach. Um, you have most of the characteristics of an apple, that 95%, but maybe as you bite into it, it's just a little bit softer, or you can just barely kind of taste the notes of a peach within that hybrid. It's the same thing with these resonance structures and kind of relating their importance. Some of them contribute more to describing the compound than others. And so what we're going to go through is a series of kind of rules, or so to speak, and these go in order that I present them, meaning an order of importance. So rule number one, you start there first. And then if nothing is different from there, you go to number two, and so on. So number one here is the most significant resonance forms have the greatest number of filled octets. So look at these two resonance forms on the left. So go from left to right, what we did here is we took a lone pair and moved it towards the carbocation, one of our common patterns. But notice the one on the left, this carbon doesn't have a full octet. The one on the right, everything has an octet. Oxygen, all the carbons. So all these atoms here still, or the oxygen still has an octet. That carbon now has a full octet. And so we say it is the major contributor compared to the one that doesn't have a full octet. We would say the same thing for the next example here. Notice the one on the left, everything has a full octet. But going from left to right, this carbon no longer has a full octet. So we would say the one on the left is the major contributor. Now, one thing I want to emphasize, notice there's one more resonance form drawn. You got that big red X there. Something you would never do is move those pi electrons there. The reason for this is you're putting that oxygen with a formal charge of +1. So that's something, notice we say insignificant. When I say insignificant, don't draw it. Now, the second way we view importance is we look at the structure with the fewest amount of formal charges. That one is more significant. So let's look at this series of resonance forms. So going from left to right, I'm going to move these here and then move these here. And then the middle one, I can move these here. And then we get the third resonance form. Now, if you look at these, they're kind of ranked. Like this one's the biggest contributor, then this one, and then this one contributes the least. Now, why is that? Well, number one, the reason it's the largest contributor is no charges and everything has a full octet. If you look at 2 and 3, they have the same amount of charges. You got a plus charge and a minus charge. Well, what's the difference between 2 and 3? 3 has 2 charges and an atom missing an octet. That's less of a contributor than something with 2 charges and everything has a full octet. So if we're just going to compare number one and two, number one and two illustrates this rule that we've been talking about. One and two both have a full octet. That's the first thing we always look for. But two doesn't contribute as much because there are two charges. Number one has the fewer amount of formal charges, so it's more significant. Now, if we look at the second example here, we just draw our arrows. I'm going to take a lone pair, move them to form a pi bond, and I'm going to move these here. Now, both of these have same characteristics, or yeah, the same characteristics. All the atoms have a full octet and only one negative charge. So we can kind of say that they almost they contribute almost nearly equally. And they describe this as a delocalized negative charge. Delocalized is a good thing because we're spreading that negative charge out to multiple atoms. Now notice again, kind of a side note here, there's a third resonance structure drawn, but again, big red X there saying don't do this because we went from one charge. If I were to go like this, I go from one charge to three charges. Not good. Every time we increase the amount of charges, that increases, I should say, decreases the stability. So that is not something that we want to show. So again, you wouldn't draw this as a valid resonance structure. The third thing we look at, again, goes in order of importance. Go one, then you look at two, number three. All things being equal, a structure with a negative charge on the more electronegative atom is more significant. So this kind of goes back to our previous example. Both of these resonance forms are equivalent in terms of they have full octet, they have same amount of formal charges, but the one on the right has the negative charge on the more electronegative atom. The carbon over here is the less electronegative atom, so it is the minor contributor. Now we do the same thing when it comes to positive charges, except it's kind of like the opposite trend. So when there's a positive charge that's moving about, like in this series of resonance forms, we want the positive charge to be on the less electronegative atom. So plus charges go on the less electronegative atom. So that's why the one on the right is the major contributor because nitrogen is less electronegative than oxygen. So that's where we want the plus charge. Now, if you go through all of these rules, 1, 2, and 3, and you don't see any difference whatsoever, it is possible for resonance forms to be equally descriptive and contribute equally. Like, for example, carbonate. All of these resonance forms, everything has a full octet, The charges are the same. The charges are always on the most electronegative atom. And so we would just say they're all equivalent. They're all major contributors to the overall structure. So let's look at some practice problems for this. So to get from A to B, I'm going to take the pi electrons in that carbon-nitrogen double bond and move them towards the more electronegative atom. That gets me to B. Now to go from B to C, I'm going to move that lone pair towards the carbocation, the atom with the carbocation to form a pi bond. Now let's go through our rules in terms of most significant, least significant, like go through like the first rule is the resonance structure that has a full octet of everything is going to contribute more. So notice B is the only one that doesn't have a full octet on that carbon. So we're going to compare C and A because C and A are going to be bigger contributors than B. So what we're doing is we're going to put B at the bottom of our list. Now let's compare C to A. They both have a full octet of all the atoms. So we're going to go to the next rule. The next rule is the more important structure is the one that has fewer charges. So C has got a full octet and no charges. A, everything has a full octet, but it's got 2 charges. So C will contribute a little more than, I'm sorry, A will contribute a little more than B, but C will have the highest contribution. All right, let's do the same thing, but now we're going to draw a series of resonance forms. So let's take a look at B. Now with B, I'm going to purposely do something wrong first. And I want you to think in your mind why I would not want to do this. One of the common trends is to take pi electrons and move them up to the more electronegative atom. That was one of our common patterns. When I write the result of this, what do you notice? I went from 1 charge to 3 charges. That's not good at all. We're not going to show that resonance form. Instead, we're going to do 2 movements. I'm going to move these pi electrons to form a double bond here, and then move those up there. So what's the result of that? Now I have this resonance structure. Now, when I compare them, are there any differences between them? Both of them have a full octet. Both of them have the same amount of charges. And the charge is on the most electronegative atom. So we would say both of them contribute equally. Neither is the major and neither is the minor. They both contribute equally. All right, so let's look at C. So notice I have a lone pair in an allylic position. And I can go either to the left or to the right. I'm just going to move this way here. I could have gone to the left as well. And so I can draw a resonance form. like this. Let's deal with our formal charges. Oxygen will be +1 because it lost a lone pair. This carbon will be -1 because it gained a lone pair. Now I can also draw one. If I start with this, I can take that lone pair, move it here, move these back to the oxygen. Actually, no, not back to the oxygen. Move them over this way. And now the negative charge would be on the opposite side. Now, just so I can talk about these individually, I'm going to label them A, B, and C. Now we start at the top of our rules. Full octets. Okay, all of them, A, B, and C have a full octet. So we go to the next rule. The one that contributes the most has the least amount of formal charges. So that's going to be A. A will contribute the most. So we would say A is most significant since it has no charges. And what can we say about B and C? B and C will contribute equally, but still be kind of a minor contributor. All right, now let's look at F. So I'm going to draw a lone pair in here on F. And I'm going to start by moving that lone pair towards that carbocation. Now I also, instead, if I go back to the first one, I could have started here at the pi electrons because that's an allylic carbocation. So let's draw what that would look like and then compare all three. All right, so we start at the top. Actually, I'm going to label these again. A, B, and C. So we start at the top of the list. The major contributor is the one that has a full octet of all atoms. So does that apply to any of them? Well, that applies to B. B is the major contributor. I don't know if that's O or E R, I can't remember. But B is the major contributor because all the atoms have a full octet. Now let's take a look at A and C. So A and C, there's a carbon without a full octet. And then each one has a +1 charge. And so we could say that A and C then contribute equally, but of a more minor contributing than B. All right, now we're going to spend a lot of time on this one in 27. So basically, what we have here are two very similar compounds. And this problem talks about something known as benzene. Benzene has this kind of template here. I want you, yeah, I'll go a lot more in depth into benzene in a later chapter. I think we don't even talk more about it until like second semester. But depending on what is attached to benzene, it could make it what's called more electron rich. So it's putting more electrons into it, or it can make it electron poor by taking electrons out of it. We can use resonance to help us predict whether that benzene ring will be electron rich or electron poor. And so that's what we're going to do here. Let's start with the first compound. I'm going to redraw it over here. And let's just start with one of our common patterns. Move pi electrons or move electrons in a pi bond up to the more electronegative atom. Now, is that it? Is that all we can do? Well, now we just kind of having a look carbocation right there. So I can move those pi electrons towards that allylic carbocation. And so the positive charge is there now. And I'm just going to highlight this. I'll come back to this, but just kind of know where that's at. Can I do anything else? Well, I just made another allylic carbocation. So I can do some more moving. And now the plus charge is there. And I can do this one more time. And the plus charge is over there. Now, what I want you to look at is notice where those plus charges are that I highlighted them. When you have those regions of positive character, that implies that that benzene ring is going to be electron poor or electron deficient. And so what I would do is like on this original drawing, I'm going to label those sites like this one here. We use that, I think that's the delta, like lowercase delta, um, with a plus. And then same thing here. That one had a plus charge in one of our resonance forms, and this one had a plus charge in one of our resonance forms. Now let's do this with the other one and see if there's any difference here. Now, does this fit one of our patterns? Well, we have an atom with a lone pair in an allylic position. So I'm going to start off by doing this movement. And then I have the same situation. I have a lone pair in an allylic position. So I'm going to do it again. And I can do that one more time. And again, I'm going to highlight each carbon inside that ring where there was a negative charge. This represents benzene as being electron rich because there's negative charges shown by resonance throughout that ring. So if I were going to use the same symbols as before, I would label this carbon as partially negative, this carbon as partially negative, and this carbon as partially negative. Now, if you were to look at each of these resonance structures, go back to our first row. Which one would you say is the most significant? Well, it would be the one that, first of all, has a full octet and no charges. So we would say this one is the most significant. We would say the same thing for the other one. This is the most significant form because it doesn't have any charges. Now, does that mean this whole problem was useless? No, what that means is that all of these other ones here were helpful in describing the regions of either positive or negative electron rich or electron poor regions around benzene. And that concept is going to become a whole lot more useful when we start talking about benzene. But the main thing I want to get across with this problem is this allows us to kind of describe how benzene will act when it reacts with other substances.